continue on 5.4. 5.3 is about the linearity test. 5.1 correlation. 5.2 simple linear regression model. 5.3 is the linearity test, and 5.4 regression analysis using Excel. Now the Excel that I'm using is Excel 2010, but now you have Excel 2019 and Excel 2016, but the procedure is the same. Okay, how you want to conduct regression using Excel? First, you key in your data. Okay, after you key in your data, you must have your dependent and the dependent variable, right? And then you go to data, choose data analysis, and then you choose regression. Okay, choose regression. Choose regression, and then you go to your you put your input data, and then you click OK. So your output will look like this. Okay, so this is the output of the regression in Excel. You have one table here. We call it as regression table. And then you have the second table here. We call it as Anova table. And last one, we have the third table here. We call it as coefficient table. Okay. So what information can we get from the Excel output? First, correlation coefficient R is your multiple R. R is your correlation coefficient. Take 4 decimal places. R square is your coefficient of determination here. Okay. Observation is the number of your data. So, from the Anova table, what information that can we get from the Anova table? We can test the linearity test. Linearity test using Anova table. This one is your F test. 49.889 is your F test. You can use this F test to conduct the linearity test using Anova table. Okay, notice that we have a new here, significant F. Significant F is your p-value. Okay, you can compare using p-value. If p-value less than alpha or p-value equals to alpha, you have to reject H null. Okay, what information can we get from the coefficient table? Here, intercept is your beta naught, number of hours is your beta 1. So, beta naught cap is equals to 26.8926. Beta 1 cap is 4.0593. So, from this, you can write down your equation, simple linear regression. Okay? So, I repeat again. The regression table, you can get R, you can get R square, and then you can get number of data. From the Anova table, you can test the linearity. Either you want to use F test or you want to use P value. Oh, here. So, I put here is P value less than alpha or P value equals to alpha. You have to reject H null. Okay, you want to use F test or you want to use P value, either one. Okay, if you want to use F test, you have to find the F critical value. If you want to use the P value, you just compare with the alpha. Okay, what we can get from the coefficient table, we can get the value beta naught and beta 1. Once you get the beta naught and beta 1 values, you can write down your simple linear regression equation. Okay, here, regression table, you can get your R square, and then the observation. Adjusted R square is actually for the multiple linear regression. Okay, and then from the Anova table, you can test the linearity. Beta 1 equals to 0, beta 1 is not equals to 0. If you want to compare using F test, you have to find the F critical value. If you want to compare the P value, you just compare with your alpha. So, you have to look at the question. The question asks you to use p-value or not. If the question asks you to use p-value, use p-value. Okay, now Okay, from the coefficient table, you can get beta naught and beta 1. Right? So, let's do the exercise. Okay, exercise 5.4 about the regression using Excel. Okay, for the same data as in exercise 5.3. So, actually, it's the same data like this. So, this data about the hydrocarbon and oxygen purity. So, the same data as exercise 5.3, the oxygen and the hydrocarbon. The simple linear regression analysis is conducted using Excel and the output is given as below. Okay, you have the summary output here. Right, so the question is from the Excel output, state the value of correlation coefficient and give comment. Correlation coefficient is R. So R is here, multiple R is your R. So R is equals to 0.9810. Interpret R. So means that R equals to 0.9810. Strong positive correlation. Okay, next. State the coefficient of determination and interpret. Coefficient of determination for simple linear regression is R square. So R square equals to 0.9624. So R square equals to 0.9624. Interpret 96.24% variation in oxygen purity can be explained by hydrocarbon. Because Y is oxygen purity, X is hydrocarbon. Done for A, done for B. Test the hypothesis that beta 1 equals to 0 at alpha 0.01. Okay, A, B, C. Linearity test. Why linearity test? Because test beta 1 equals to 0. So, beta 1 is linearity. So, step number 1. H null beta 1 equals to 0. H1 beta 1 is not equals to 0. So, for step number 2, I want to use Anova. So, from this Anova, I want to use significant F, where significant F is your P value. Okay, so P value is equals to 1.6897 times 10 to the power of negative 5. So, it's actually 1.6897 times 10 to the power of negative 5 or 0.12345. 0.0000. So, P value is equals to 0.0000. Then, since P value equals to 0.0000 less than alpha 0.01, we reject H null. So, what will happen if you reject H null? At alpha 0.01, beta 1 is not equals to 0. There is a linear relationship between hydrocarbon and oxygen purity. Okay, done for C. D, state the equation. So, the equation we can get from here. Okay, this one is beta 1, beta naught. This one is beta 1. Okay, beta naught cap equals to 74.6224. Beta 1 cap equals to 14.7055. Then you write down the equation. The equation will become Y cap equals to 24.6224 plus 14.7055x. Okay. use the estimated simple linear regression model. So use this model to predict purity of oxygen when 2% hydrocarbon present. So use this equation. They ask you to predict Y when they given you X is 2%. So you just substitute X into this formula. Okay. X equals to 2. So 74.6224 plus 14.7055. You put 2 there. Okay. And then you substitute into the calculator. The answer will be 104.0334% oxygen purity produced. Okay, that's it.